Okay, so welcome everyone to today's one-word IAMP mathematical physics seminar. This is a regular event hosted by IAMP, the International Association of Mathematical Physics. And if you're watching this on YouTube, and if you're new to this seminar series, please click the M_5 logo you see down there, and then you will find more about the seminar and also about the IAMP. And please think about joining our mailing list or to IAMP. Okay, so today it is our great pleasure to have Claude-Alain Pillet, and he's going to tell us about their recent work on adiabatic time evolution. Okay, Claude-Alain, the floor is yours.
Thank you, Hal, and thanks to the organizing committee of this seminar series. I think the community is really grateful for the great work you're doing. Today I'm about to present some results that belong to the second part of a joint work with Jaksic and Tauber. The first part of this work was the subject of Stokes in the same series of seminar 2 years ago. And it was concerned about the structural properties of quantum system featuring approach to equilibrium. So, you have on the slide, on the title slide, you have the title of the two papers. I may refer to these two papers as paper 1 and 2 in the following. So the two papers appeared in the January issues of Henri Poincaré, who was a special issues in memory of Christoph Kawecki. The research program that was initiated in these two papers, 1 and 2, is actually strongly inspired by the success of the algebraic formulation of quantum statistical mechanics in dealing with certain problems like return to equilibrium or relaxation to non-equilibrium steady state in the last, I would say, 20 years. The main object of the two papers was to derive properties of translation-invariant quantum dynamical system that do not depend on the fine details of these systems, but really just on the general structure. In this second part, second paper, we consider a quasi-static process performed on extended spin systems on a lattice, or if you prefer, on fermionic systems that are described by slowly varying non-autonomous translation-invariant interactions. And the emerging structural theory yields in particular that a realization of such a quasi-static transition is possible only if the specific entropy remains constant during the whole process. As we shall see, it is combined with the result that Voigtland described in the first, in his seminar about the first part. So this implies in particular that in this setting, translation-invariant quantum systems, adiabatic limits, I mean the adiabatic theorem and the quasi-static transition that they describe are incompatible with approach to equilibrium. So the plan of the talk is here. After a short introduction, I will describe in more details a special case that is what has been done in the last 20 years, I would say, on local perturbations. I will then present the setting of the present work on translation-invariant perturbations. I will need to recall a few things about that were the subject of Voigt and Stokes, and then I will speak about the main object of this talk, adiabatic evolution in translation-invariant system, formulate our main results, make some remarks, and end with some references. So I will start with a short reminder about what we call adiabatic theorem in quantum dynamics. That's something that goes back, at least in the old theory, to Born and Fock, and in fact even to Ehrenfest. But it was only formulated in the current functional analytic terms of quantum dynamics by Toshio Kato in the 50s. So it concerned a non-autonomous Schrödinger equation that I can write like that. So I have an Hamiltonian which actually depends on some parameter between 0 and 1. So real time is a small t in this equation, and big T is what we call the adiabatic parameter. So the equation holds for t between 0 and big T. And we are interested in the behavior of the solution of this equation as big T tends to infinity. That means when the Hamiltonian varies very slowly. Okay. And the best thing to do is to rescale the time in this case and to introduce the rescale times s, which varies between 0 and 1. By multiplying s with t, we recover the real time. And in doing that, the Schrödinger equation transforms into this form. Okay, so we have a 1 over t in front of the derivative. So the main point of the adiabatic theorem, I will not enter too much details, but assume that the initial state phi 0 is an eigenvector of the initial Hamiltonian H0. Then, under appropriate conditions, one can look at what happens with the solution as the adiabatic parameters tend to infinity, and one finds that as t goes to infinity, at rescale times s, the solution converges to an eigenvector of the instantaneous Hamiltonian corresponding to the rescale time s. Since Kato, there have been many more refinement. There have been many refinement of Kato's result. I mentioned a few of them here. They deal with either rougher spectral decomposition, not focusing on an initial state which is an eigenvector, but which could belong to some part of the spectrum which is separated from the rest. They also deal with better control of the convergence, and some of these results gives even exponential rates for the convergence. Very important for us is as a contribution by Aaron Elgaard, which actually succeeded in removing one of the major conditions in Kato's work, which was a spectral gap assumption. And I mentioned also last work by Avron, Frass, Graf, and Resch, who generalized that to non-unitary evolution, more generally contractive dynamics, such as quantum Markov surrogates. I also refer to the nice book by Stefan Teufel, who reviewed all these things. So this was really adiabatic theorem for the Schrödinger equation for, I would say, one particle quantum dynamics. The extension to many body quantum dynamics is important too. I will mention a few results in these directions. First, the easiest case, which is the case of local perturbations of these dynamical systems, where one just look at what happens when an autonomous quantum dynamical system is perturbed by a gentle time-dependent term, which I will in the next slide I will give more details on that. But, so here I mentioned two results, and an early one by Naunhofer and Thiering, who actually approached the problem through scattering theory by making some restricted asymptotic abelianness condition, which are known to be very difficult to check in practice. The other series of work concerned isothermal adiabatic theorem for extended quantum systems at positive temperature as a model for quasi-static processes. So I mentioned here the early work by Abu Salem Fröhlich and a more recent work on the Landauer principle by Woyken and myself. So this is an easy case, so to say. More difficult case is the case of spatially extended perturbation. There one needs some gap assumption to get the result. So at zero temperature, one has a very recent result by Bachmann, Derek, and Frass, which tells something about convergence of the expectation values of some local observables in the adiabatic limit. This was done for spin systems. This has been extended to fermion systems by Monaco and Titile. But this is the main point is this is at zero temperature. This was ground states of this system. The positive temperature case was treated in a very recent work by Greenblatt, Lange, Marcelli, and Porta, and actually the result of this. I mean, they give a very precise estimation, and this estimation seems to point out that at positive temperature, it's not so clear that one really has an adiabatic theory. I will maybe comment a little bit later on that. So here I come back to the easiest case, because this will serve as a motivation for us. Let me just see. So okay, so the main setting for the local perturbation case is here. So one has a C-star dynamical system. That means one has an algebra, a C-star algebra of observable on which a strongly continuous group of star automorphism act as the Heisenberg dynamics on this algebra of observable. And I have a state. So in this setting, a state is just a linear functional which is positive and normalized. And for the discussion below, I will assume that this state is a thermal equilibrium state, which in the algebraic setting translates into a tau KMS state. And in the whole talk, I will actually fix the temperature. I will always have an inverse temperature beta equal to 1. I will make a comment on that restriction in the end, but this is not a restriction. This is just something that one can always do. So what is a local perturbation? One has a group of dynamical transformation, tau t, which is generated by a derivation delta. And one pick a self-adjoint element of the algebra, V, which is going to be our perturbation. And what one perturbs is a generator of the dynamics by adding to delta the I times the commutator with V. So this gives a new group of Heisenberg dynamics on the system. Now, by Araki's perturbation theory of the KMS structure, there is a non-continuous map which transform a self-adjoint element V of the algebra into a state rho V. The state rho V is characterized by being a KMS state, so thermal equilibrium state at temperature 1 for the perturbed dynamics. And now I will actually use this rho V to define what I call the property of return to equilibrium. I will say that my dynamical system O tau rho has the property of return to equilibrium whenever starting the system in a perturbed state rho V, running it with the dynamic tau after a time averaging I will get something which goes back to the initial equilibrium state rho. And this should be true for all perturbation, all self-adjoint perturbation V, and of course for all A. Okay. Now I will be interested also in non-autonomous local perturbation, in which case V will be replaced by a time-dependent self-adjoint element Vt, and I will consider the adiabatic limits, namely rescaling. I mean, rescaling time as in the Schrödinger case. I will consider the time evolution generated by this equation here. Okay, so this will describe in this limit t to infinity. This will describe a quasi-static process on my system. So this was, yeah. So let me just here. Sorry. Let me just here formulate what I will call the adiabatic theorem for this local perturbations. So I choose the version of the theorem proved by Roykan and myself in this paper I mentioned before. So one consider a dynamical system O tau V, which is such that a time-dependent perturbation V of S, okay, which has the property that all the perturbed dynamical system O tau Vs, Rho Vs have the property of return to equilibrium. For Lebesgue, almost all S in 0, 1. Then one can show that. So here we maybe start to set up the name I will give to objects. So here rho V naught is the initial state, okay, and this is the time evolution. So we'll call rho V naught time evolved to time t. I will call that the time evolved state of the system. And rho Vt, this is a thermal equilibrium state for the system, given that the system is perturbed by the local perturbation V of t. Okay, so I will call that the instantaneous state at time t, the instantaneous equilibrium state at time t. So what's the adiabatic theorem tells me is that uniformly in t, as in the small time parameter, as the parameter big T goes to infinity, one has convergence of the time evolved state to the instantaneous state at any time in the norm. Okay. Now, entropy is going to play a central role in this talk. So let me now introduce this notion of entropy. I will start with the notion of relative entropy. So for density matrices, relative entropy is just defined by the usual formula. Relative entropy of mu with respect to rho is trace of mu log mu minus log rho. In the infinite dimensional case, there is a more complicated formula, but I will not use it. Let me just mention that there is a formula that was proposed by Haraki, which gives the extensions of this concept. What is important for the following is that this relative entropy satisfies an inequality, the Pinsker-Zizach inequality, which tells that the relative entropy is bounded below by a constant times the square of the norm distance between the state. Now the next result is a kind of complementary relation to this inequality. Suppose that again we have a time-dependent perturbation V of S, which is C1. Then one can prove the following what we call entropy balance relation, which tells us how this relative entropy of the time evolved state with respect to the instantaneous state changes with time. And this is a very simple formula which tells us that this is just the integral of the expectation value of the time derivative of the perturbation with respect to the linear functionals, which is given by the difference between the time evolved state and the instantaneous state. Now, armed with these two, with this inequality and with the formula, it is very easy to derive the corollary 3 here. Again, supposing that V is a C1 local perturbation of my dynamics, I have equivalence between these 3 forms of adiabatic theorem. The first one is that for Lebesgue, almost every time t in 0, 1, one has convergence of the expectation values of the derivative V dot in the time evolved state towards its expectation in the instantaneous state. The second is that the relative entropy of the time evolved state with respect to the instantaneous equilibrium state goes to 0 as the parameter big T goes to infinity. And finally, one has convergence in the sense of the usual theorem that the time evolved state converges to the instantaneous state as big T tends to infinity. So this
can I ask a question?
Yeah.
So so about this theorem 1, is this equation correct? You have A here on. So inside the limb soup, you have rho, circle, alpha, and you have uppercase A. What does this A mean?
Which one?
At the equation at the top.
At the top here, yeah.
Yeah. So you have alpha and you have A, uppercase A here.
Oh, sorry, there should be no A here, of course. There should be no A, I'm sorry.
Okay.
This is a typo.
So
There should be no A. This is a norm of the difference of two states.
Right. Yeah.
Thanks. Okay, so this was the setting for local perturbation. I will now introduce the setting for translation-invariant system, but I will come back to, corollary 3 will pop up at the end, because we will see that one has a completely similar statement in the translation-invariant case. So here is the setting for the translation-invariant system. So I will restrict myself in this talk to the spin case. One can of course easily translate all these things in the language of fermions, but for simplicity I will skip to the spins. So we'll use the usual languages that you can find in many textbooks now. Here is a list of monographs where all these things which were developed in the 70s are explained. So I will have a single spin Hilbert space, which is just a finite dimensional Hilbert space, C to the n, and the same space for all site x in a d-dimensional lattice, C to the d. So F will denote the set of all finite subset of the lattice, and for any of these finite subset, I define the local Hilbert space Hx, which is just the tensor product of the one-side Hilbert spaces. The algebra Ax is just the algebra of bounded, of linear operator on this finite dimensional Hilbert space Hx. So local, realizing that if X is a subset of Y, then one can identify AX as a subalgebra of AY. Then one can take the union of all the AX. This is what I will call the local algebra. and taking some inductive limit, or just taking the norm closure of this local algebra with respect to the norm induced by all X, one get a C-star algebra, which will be our spin algebra on which I will work. Okay. So in this spin algebra, there is a natural action of the translation group Z to the D. Okay, and this transforms the local algebra AX into AX translated by small x. Now, an interaction for my spin system is a family of self-adjoint operator indexed by the finite subset of the lattice. I will always assume that this interaction is translation invariant, so that if I translate phi x, I get phi x plus x. And I will assume that this interaction belongs to some nice Banach space of short range interactions given equipped with a norm which is just the sum of the local norms weighted with an exponentially increasing factor. So here modulus of x is just, of course, the cardinality of the set x, and R is some positive parameter. Given the interaction phi, one introduced for any finite box lambda on the lattice centered at 0, I introduce the local Hamiltonian, which is just the sum of the interactions for all the finite subset of the box. Given this local Hamiltonian, one defines, I mean, using the unitary group generated by this self-adjoint local Hamiltonian, one defines dynamics, and one can show that for any element of the local algebra A, this thermodynamic limit here exists as the box lambda tends to the full lattice. One get a limit which is of course isometric, and so it extends by density to the full C-star algebra A. So this describes how one goes from an interaction phi to a dynamic star phi. I mean, this map is not 1-to-1, and you may eventually have two interactions which generate the same dynamics, in which case one will say that these two interactions are physically equivalent. This is a concept which will be important in the end for us. Last point in the setup, we will only consider translation invariant states. Okay, so states which are invariant under the action of the translation group. And given such a translation invariant state and a finite box lambda, I will denote by rho index lambda as a restriction of rho to the finite dimensional algebra associated with the box lambda. Since this is a finite dimensional algebra, this means that rho lambda is actually described by a density matrix on the Hilbert space H lambda. And so I can define the phenomenal entropy of this restriction as minus trace rho lambda log rho lambda. Now it turns out that normalizing this entropy with the volume of the box. Okay, so that means computing the entropy per spin. Actually, this quantity has a limit, has a thermodynamic limit, okay, which I will denote by small s of rho. So this is, strictly speaking, the specific entropy of the state rho. It is an upper semi-continuous function. This will be very important for us. So it is, I will call specific entropy, but in order to limit the number of words that I'm going say in the following. I will in the following I will just call it entropy. Okay, I will. This entropy will never occur again. So when I will call something entropy, I will always be speaking about a specific entropy, and the same for the energy. Okay, so given an interaction phi, if I sum over all the finite subset containing 0, phi of x divided by the number of spin on x, so this is just the energy per spin induced by the interaction phi, and so E phi is just the total energy per spin, so it should be called the specific phi energy, or the specific energy of the interaction phi. It has this property that its expectation value in a translation-invariant state rho is equal to the thermodynamic limit of the expectation value of the total energy per spin when computed in a finite box. So for the same reason as for the entropy, I will just call this quantity, I will call that the phi energy in the state rho, instead of the specific phi energy in the state rho. And the last players in the game will be the pressure of the interaction phi, given that, as I said before, I will restrict myself to inverse temperature beta equal 1. This pressure is a supremum over all translation-invariant state rho of the difference between the entropy of rho and the phi energy of rho. This is called the Gibbs variational principle, and the states which maximize this variational principle, they are called equilibrium state at inverse temperature 1, and I will denote the set of such states as S equilibrium of phi. Okay, so this is a non-empty convex subset of the state of the set of translation-invariant state. And to make connection with the KMS state that I mentioned before, these equilibrium states coincide with translation-invariant KMS state for the dynamic tau phi, but I will not really use that in the following. Now, following the strategy that have been used, for example, to define the non-equilibrium steady states for local perturbations of C-star dynamics, I will call the steady state any weak star limit point of the net of states, which is described by this formula. So one start with here. I really specify. I'll start with an equilibrium state rho for some interaction psi. I suppose that I have another interaction phi which is not physically equivalent to psi, so that the dynamic tau phi does not necessarily leave rho invariant. Okay. Now I let my equilibrium state for psi, I let it evolve with the dynamics of phi. I average that over the time, over a large time interval from 0 to big T, and I see what happens when big T tends to infinity. I denote by S plus phi rho the set of limit points of this net. It's clear that any element of this set is a tau phi invariant state, so it is a steady state for tau phi, and it is also translation invariant. Moreover, one has conservation laws. That was the first result is due to Lanford and Robinson, that the entropy of the state rho T is always equal to the entropy of rho. And we proved that the same is true for the phi energy. The phi energy in the state rho T is equal to the phi energy in the state rho. So what does that mean for any element of for any steady state, or any element of the set of limit points of this net? Well, it really means that the phi energy of such a state is equal to the phi energy of the initial state rho, and because rho of something is a continuous function of rho, okay? And because remind you that the entropy is upper semi-continuous, this means that it may not actually remain constant in the limit, but that it cannot decrease. So the entropy of rho plus cannot be smaller than the entropy of rho. Now, I want to characterize what I will call approach to equilibrium. So what would I mean by approach to equilibrium in this setting? So if rho is not tau phi invariant, so that rho t in general will not remain constant, I will say that approach to equilibrium holds for the pair of interaction phi and initial state rho if I can find in the set of steady states an equilibrium state for phi. Okay. So this is a loose way of characterizing approach to equilibrium. Of course, you would like to know much more, but even that is very difficult to prove in specific cases. So Ruel actually considers the question about this inequality. I mean, so since by Lanford-Robinson one has constancy of the entropy along a trajectory. Is it possible that given that one has approach to equilibrium, one has actually a strict increase of the specific entropy, so that the specific entropy of the equilibrium state rho plus is strictly larger than rho. Okay, and now I will give the answer to that, which was one of the main results in the talk of in Voiken's talk. So for this I will need this. Can I move that? Okay, I can move that. I can move that away. So to formulate the result, I will need this notion of weak Gibbs state that I define now. So a translation-invariant state rho is a weak Gibbs state for the interaction phi if one can actually bound the density matrix describing the restriction of rho to a finite box lambda. One can sandwich that between simple multiple of the Gibbs weight given by the local Hamiltonian. So here one has rho lambda smaller equal or constant e to the minus h lambda of phi. So this is the Gibbs factor minus the volume of lambda times the pressure of phi, and the same thing in the lower bound. Okay. With a constant 1 over c lambda, and the condition is that the log of c lambda divided by the cardinal of lambda goes to 0 as lambda tends to infinity. And I will denote by Vg of phi the set of weak Gibbs states for phi. Now, given these inequalities, it is very simple to prove the following proposition: for any state rho weak Gibbs for phi, and for any translation invariant state mu, if one compute the relative entropy of mu lambda, so the restriction of mu to the box lambda, with respect to the restriction of rho to the set lambda, divided by the volume of lambda. So this is just a relative entropy per spin. This has a thermodynamic limit as lambda goes to infinity, which I will denote by small s of mu of rho. Okay. In the following, I will just call that the relative entropy of mu and rho. Even so, it is only the specific relative entropy. Moreover, this relative entropy is equal to the phi energy of mu plus the pressure of phi minus the entropy of mu. Now, this quantity, as I've seen before, it's non-negative, and so the limit is non-negative. So the relative entropy of mu with respect to rho is a non-negative quantity. And what does it mean that it is zero? If it is zero, this means that this is zero, but this just is a characterization of mu as an equilibrium state, because this says that mu is a maximizer of the Gibbs variational principle. So S of mu rho is zero if and only if mu is an equilibrium state for phi. It is clear from that any weak Gibbs state phi is an equilibrium state for phi, because if mu is equal to rho, this is zero. Okay. In the classical commutative context, we know that any weak Gibbs state, that any equilibrium state is a weak Gibbs state. This was proved by Pfister and Sullivan in 2019. So this is our conjecture that the set of weak Gibbs state for phi, given that phi is a translation invariant element of this Banach space BR for some R positive, is equal to the set of equilibrium states for phi. We are not able to prove this conjecture in general, but we know that it holds in dimension 1 if the interaction phi is finite range, or in dimension bigger than 1 if the norm of phi satisfies this inequality, which means that we are in a large temperature regime. Now, one of the main results in Wolkenstock on the first part of our work is that for any pair phi rho, where phi is an interaction in BR and rho a translation invariant state, if one has, in the sense that I introduced before, approach to equilibrium, namely that there is a state rho plus, which is a steady state for phi, for the interaction phi starting with rho, and the weak Gibbs state for rho, then one has this equivalence rho plus difference from rho if and only if the entropy of rho plus is strictly bigger than the entropy of rho. I recall you that the entropy of rho plus cannot be smaller than the entropy of rho. So another way to formulate that is rho plus equal rho if and only if S of rho plus equal S of rho. Okay, so when one has approach to equilibrium, then either the equilibrium state is equal to the initial state, which means that the initial state was actually invariant with respect to the new dynamics, okay, or the entropy strictly increase as we approach equilibrium. We have a strict increase of the entropy as we approach to equilibrium. Now, now let me go to the adiabatic evolution. So I will proceed as in the local interaction case, given to any rescale time t between 0 and 1, I associate now an interaction phi t. And I assume that as a function of t, this is a continuous function from 0, 1 to my Banach space of translation invariant interaction phi r. Given such a family, I can, of course, associate to that family of local Hamiltonians as before. And I can consider the dynamics generated by this time-dependent local Hamiltonian, which satisfy this equation with the adiabatic scaling 1 over t, 1 over big T, okay, which means that as big T goes to infinity, I am describing an adiabatic time evolution. It is not very difficult to extend the result of the about existence of the dynamic in the time independent case to the time dependent case. One can show that this set of local time evolution has a thermodynamic limit as the box lambda goes to the full lattice. It exists first for all local observable, and it extends again by density continuity to all element of A. this dynamics commute with the action of the translation group CD on the algebra A. The map which to the scale time t associate alpha t as an element of the star automorphism of alpha is a strongly continuous map which satisfy the differential equation given here with a generator delta phi t, which is just given by the usual formula. Moreover, one can extend the Robinson, the Langford-Robinson result that was mentioned before, so constancy of the entropy, one can extend that to the time dependent dynamics. Okay, so the entropy of a state is invariant along the trajectory generated by this dynamic. And of course, the limit big T to infinity correspond to what I will call the adiabatic limit. Now we'll introduce a few wording about this limit, which I will use in the next to formulate my result. I will call the path, and I will denote it with this notation, a continuous map from the interval 0, 1 to pairs of elements phi t interactions in the Banach space BR, and state rho t, which are translation invariant state, and I will assume that this rho t is actually an equilibrium state for phi t. So such a path is a family of a pair of interactions and equilibrium states for these interactions. And I will call a pair interactions equilibrium state, I will call it uniquely regular whenever the set of equilibrium states for phi is a singleton containing only a state rho, and that this state rho is weak Gibbs. And the path itself will be called uniquely regular whenever for all t in 0, 1, the pair phi t rho t is uniquely regular. Yeah. Now, I will say that the adiabatic theorem holds for the path phi rho whenever the time evolved state rho 0 evolved to time 1 by the adiabatic time evolution converge in the adiabatic limit to the instantaneous equilibrium state at time 1. Okay, I will call that the path adiabatic theorem holds if this is true not only at time 1 but at any time between 0 and 1. Okay. Then I will say that the entropic adiabatic theorem holds whenever the relative entropy of the time evolved state at time 1 relative with respect to the instantaneous state at time 1 tends to 0 in the adiabatic limit, and the path entropic adiabatic theorem holds for the path phi rho if this is true for all time. Okay, and now I'm ready to formulate my main result. Suppose that the path phi rho is such that the final element phi 1 rho 1 is uniquely regular. Then the following statements are equivalent. First, the entropy of the final state is equal to the entropy of the initial state, and the adiabatic theorem holds for the path phi rho. Second, again, entropy of the final state is equal to entropy of the initial state, and the phi 1 energy in the time evolved state approaches in the adiabatic limit the phi 1 energy in the instantaneous final state rho 1. Last statement is that the entropic adiabatic theorem holds for phi rho. Now, the proof of this is so simple that I cannot really resist in giving the proof here. So the first implication is trivial, okay? Because saying that the adiabatic theorem holds for phi rho means that this is true for any local observable. So in particular, it will be true for the observable E phi 1. Now, to prove that 2 implies 3, okay, so we start with fact with this formula for the relative entropy. Okay, so we know that by assumption ρ1 is a weak Gibbs state, and so the relative entropy of the time evolved state with respect to ρ1 satisfies the formula that I wrote before. So it is the phi 1 energy in the time evolved state plus the pressure of phi 1 minus the entropy of the time evolved state, but remind that the entropy is constant along the path, so that the entropy of this state here is actually equal to the entropy of ρ0. Okay. Now look at what happens when big T tends to infinity. Since I assume that 2 holds, okay, I know that this quantity here converges to this one. Now this equation and this quantity here is just what characterizes the fact that ρ1 is an equilibrium state for phi 1. Okay, if ρ1 is an equilibrium state for phi 1, this means that this is 0, and so the limit of this quantity is 0, which means that the entropic adiabatic theorem holds for phi ρ. Now, the most difficult part is to prove that property 3, so the entropic adiabatic theorem holds, implies that the adiabatic theorem holds. Okay, so for that, assume that I have a state ρ plus, which is the weak star limit point of this set of this net of states. Okay. Now I know that the function that to mu associates the relative entropy of mu with respect to ρ1 is lower semi-continuous. And this relative entropy is non-negative. And since it is lower semi-continuous, means that S of the relative entropy of the limit is smaller or equal to the limit of the relative entropies. But by the entropic adiabatic theorem, I just know that this limit is 0. This quantity actually converges to 0, so the limit is 0, and so I know that S of ρ plus ρ1 is 0. Okay, but remember that for a translation invariant state, having a relative entropy with respect to a weak Gibbs state means that the state is actually an equilibrium state. So ρ plus is an equilibrium state for phi 1, but I assume unique regularity. So I assume that there is only one state which is equilibrium state for phi 1, and that the state is ρ1. So what I have proved is that this net actually converges to ρ1. Now, again, writing again the expression for the relative entropy of the time evolved state with respect to the instantaneous state at time 1. Okay, so this is again the phi 1 energy in the time evolved state plus the pressure of phi 1 minus the entropy of the time evolved state, which is equal to the entropy of the initial state, the same as before. If I take T to infinity, now I know that this quantity here converges to the phi 1 energy of ρ1 plus P of phi 1 minus S of ρ0, but I know that ρ1 is an equilibrium state for phi 1, so I know that this quantity here is nothing but the entropy of ρ1. And so this is S of ρ1 minus S of ρ0, and it is 0. Okay, and so this means that this is true, and that the adiabatic theorem holds for phi ρ. So an immediate consequence of this is that this was specified for the time t equal 1. Okay, now I can t equal 1 is no special. So suppose that now that the path is entirely uniquely regular, so that the conditions of the previous theorem holds not only at t equal 1, but but at any time between 0 and 1, okay, then the conclusion of the theorem also holds at any time between 0 and 1, okay, and so one has this the same theorem as before, except now that all the statements are for all times between 0 and 1. And now, using this corollary, one can prove the next theorem, which is actually the translation-invariant version of the corollary 3 that we had for time for local perturbations of the C-star dynamics. Okay, I promise you that this corollary 3 will pop up again. So here it is. This theorem 1 says that assuming again that one has a path phi rho which is uniquely regular and C1, then the following are equivalent. The path entropic adiabatic theorem holds. The path adiabatic theorem holds. And for Lebesgue, almost every time, the limit as t goes to infinity, I mean, as the adiabatic parameter tends to infinity of the. Here I have to. Here first I have to notice that. So this is the phi t energy, okay? So the specific energy of the interaction phi t. Now I want to know how this evolves in time, so I derive with respect to t. But remember that E phi t is a linear expression of phi t, and so the time derivative of E phi t is just E phi dot t. Okay, and so here, this is a quantity which enters in this condition here. So the time evolved expectation of E phi dot is equal to the instantaneous expression, the instantaneous expectation value of E phi dot. And any of these three statements implies that the entropy of rho t is actually equal to the entropy of rho 0. So unfortunately, I thought I could give you the proof. The proof is not. The proof is almost as simple as the proof of the previous theorem, but I will not have time to go through it. So I will leave it to you to read it here. I will end up with a simple application of this last theorem to the quasi-static, to the relation between quasi-static process and approach to equilibrium. So suppose now that we have two pairs phi 0 rho 0, phi 1 rho 1, which are uniquely regular. So rho 0 is an equilibrium state for phi naught, and a weak Gibbs state, the same for rho 1 and phi 1. Assume that the two interactions phi 0 and phi 1 are not physically equivalent, so they have different time evolution. Then the following statements are mutually exclusive. First, one has approach to equilibrium for the pair phi 1 rho 0. Okay, meaning that if I evolve rho 0, which is an equilibrium state for phi 0, but I evolve it with the dynamics of phi 1, I get a limit point, which is actually an equilibrium state for phi 1. So this is approach to equilibrium. And the second statement is that there exists a path, phi rho, which goes from phi naught rho naught to phi 1 rho 1, and for which the adiabatic theorem holds, meaning that rho 1 is the adiabatic limit of rho 0 through the adiabatic time evolution. So these two things are mutually exclusive. Either one has approach to equilibrium, then one cannot have an adiabatic path between the two states rho 0 and rho 1, or one has an adiabatic path, and if we have an adiabatic path between rho 0 and rho 1, then approach to equilibrium cannot hold for rho 0 and phi 1. Okay, and again the proof is very simple, but I prefer to finish in 2-3 minutes by giving some remarks rather than going into the proofs. So first remark is about our idea of fixing the inverse temperature to beta equal 1. I want to convince you that this is not a restriction. So this inverse temperature will appear at 2 different places. It can occur for, I mean, it occurs for the initial state. So rho is supposed to be an equilibrium state of phi, meaning actually beta phi. Okay, so if beta is different from 1, one can just absorb it in phi. Okay, so these changes, S equilibrium of beta phi depend on beta. Okay, but what does not depend on beta is a set of steady states that you reach from rho with the phi, because multiplying phi with beta in this case is just rescaling time. Okay, so I can always suppose that my equilibrium state is an equilibrium state at inverse temperature beta by properly rescaling the interaction phi. Well, the second place where the temperature occurs is when saying that rho plus, when characterizing approach to equilibrium, saying that some steady state rho plus is actually an equilibrium state for phi. So it could be an equilibrium state for beta phi for some beta. Now, knowing that as beta varies, these equilibrium states form a family of mutually disjoint states, rho plus can only belong to one of the set as equilibrium of beta phi. Okay, so for example, rho plus will belong to this something like that with beta different of 1. But then rescaling phi to beta phi will set the temperature of rho plus to 1. Okay, so this will settle the question. Now, our main result relies on this crucial assumption that phi has a unique equilibrium state, which is actually a Gibbs state. Now, there are well-known criteria to characterize uniqueness of the equilibrium state. In dimension 1, for example, one has this condition proved by Araki in 1974. In dimension bigger equal 1, there are many results in this, and here I mentioned one of the most recent one by Daniel and Jörg. So this condition physically can be translated as being a high temperature regime. Okay. Now the second condition is that any equilibrium state is that this equilibrium state is weak Gibbs. Okay. Now that's much more difficult due to your poor understanding of Araki's Gibbs condition, which characterize equilibrium state. This is still an open conjecture in general. So in our paper we give two cases where one can show it. In dimension 1, if phi is finite range, and in arbitrary dimension, again, this is a large temperature assumption. If one can find some positive R such that the R norm of phi is smaller than R. Okay, so this means that our main assumption is satisfied either for finite range interaction in one dimension or at high temperature in arbitrary dimension. Okay. A remark about a bosonic system. I mean, I already mentioned that all what is done in the setting of spin can be translated in the setting of fermions. One just have to discuss gauge invariant, which is not very difficult. Much more difficult, I think, is the case of bosonic system, because one has to deal with W star dynamics, which is much more difficult to deal with. Yeah, I mean, this is the last remark is that algebraic quantum statistical mechanics provides a very natural mathematical framework for the study of dynamical aspects of quantum system, and in particular, infinitely extended quantum system. It has many successes, starting in the 70s with the development of equilibrium theory, but also more recently with many results in non-equilibrium theory. But at the moment, it remains completely unknown whether this framework can even in principle account for the zeroth law of thermodynamics, so for approach to equilibrium. So much remains to be done in developing a general structural theory and studying concrete physical model in the context of this talk. Okay, so I finished with a short list of the references that I mentioned in this talk. For a complete list of references, you should look at the papers. Thank you.
Oh, thank you very much, Claude-Alain, for the very interesting talk. So now it's time for questions, and Benjamin has a question.
Hi, Claude-Alain. Thank you for the nice talk. Yeah, so it seems to me this condition of approach to equilibrium is quite strong, and probably too strong. And I think it will be impossible to prove, because if you have other conserved quantities, then you don't expect to approach the equilibrium state determined by the phi of the time evolution. You expect to approach something determined by some, conserved some other Hamiltonian that.
Yeah, I understand what you mean. Yeah.
Yeah.
Yeah, of course, you're probably right. I mean, one should. I mean, one way would be to restrict the set of observable on which you require convergence. Otherwise, I mean,
Yeah.
Of course, you can always find examples where you have conserved quantities which will break these things. That's for sure. On the other hand, I mean, along the same kind of ideas, what I found very disappointing is that it is believed, I mean, the general belief is that the approach to equilibrium is actually due to interactions, but the only system in which one has a rigorous proof of approach to equilibrium are systems in which there are no interactions, quasi-free systems.
Yes.
So this really shows the bad status of this question. I mean, so
Yeah,
this is really just the first thought in direction of I would say structural approach to these questions.
But probably we better to kind of formulate it by saying approach to some space determined by R.
Yeah.
That probably one can show more generally, but that for this one you have to know the concept of quantities. You have to know the model is integrable, and that's mathematically very difficult, I think.
Exactly. Yeah.
Thanks.
I agree. Yeah.
Any other questions or comments? Okay, let me ask one rather stupid question. So what is the main message of your main theorem about this dichotomy? Or
the main message is, I think the main message is a very general one, namely one can get interesting hints about what is going on by, I mean, to get some interesting insight into what is going on. One does not necessarily need to dig into all the details. You know, if you really want to prove something like approach to equilibrium, you need infinitely precise estimates on the dynamics, and so you really need to go into all the details. What we have been using are just very general global structure of this system. basically,
but
basically we only use the variational principle. And,
yeah.
so I think that's the main message, is that
Oh yes.
since
But
since this question is so difficult, maybe one should not think first to very delicate questions, but try to find more general arguments which are just based on the general structure of the problem.
Oh yes, but I was more specific about your main theorem. It says that you cannot have the approach to equilibrium
Yeah.
and
So
adiabatic theorem at the same time.
So what I suspect is that there is actually a problem with adiabatic limit at positive temperature. I suspect that actually there is no general result in this direction, and I must say that. So I mentioned this paper by Greenblatt, Lange, Marcelli, Porta, where they actually try to get estimates on what is going on at positive temperature when one has an adiabatic evolution, and the estimate they get, which is one of these, very precise, and they use very sophisticated approach to the dynamics, but the estimate that they get leaves the room for the non-validity of the adiabatic limit in this.
Okay, so I think I understand that you have shown that in order to have adiabatic theorem, your specific entropy cannot change. And you're saying that it's a very strong restriction, which means that adiabatic evolution may be very difficult or impossible in this case. Okay. Very interesting. Any other questions or comments? Okay, if not, let's thank the speaker again. Thank you very much.
Thank you.
Thank you. Thank you for the nice talk.
Thank you.
Thank you all.